I'd like to spend a few minutes in this video talking about the relationship between bond strengths in molecules and the enthalpy change that one finds in a reaction. I think it hopefully is fairly evident to you that the major source of enthalpy changes in reactions really has to do from the fact that there are different bond strengths in the reactants and the products. So when we change the bonds, when we rearrange valence electrons, change the bonds to go from one set of chemical species to another set of chemical species, a logical place to look for that enthalpy change is going to be in the strengths of those bonds. Now let me illustrate this with a simple example, and we're going to beat this example to death, so I hope it's a reaction you like. It's going to be a very simple reaction. I want to just consider the synthesis of water from oxygen and hydrogen. Now, we talked about this a little bit in another video. Now, if I were to look at this purely from a construction standpoint, what I have to do in order to get from these reactants to these products is the following. I've got to start off with 2 molecules of hydrogen, and I'm going to have to break those bonds. I'm going to have 1 molecule of oxygen, I'm going to have to break that bond. And then when I put all these things back together, I'm going to end up creating 2 water molecules, which basically consist of 4 equivalent OH bonds. So it's a fairly simple process. I mean, I hope that most of the reactions you deal with in the lab are more complicated than this. This is a fairly simple process where we're going to break 3 bonds over here and create 4 bonds over here. And unsurprisingly, the net result of this process is a negative enthalpy change. That is to say, we're going to release energy. And I want to make sure that we understand that when we break bonds, we are engaging in a process that actually creates an enthalpy change that is greater than 0. We have to add energy in order to break bonds. When we create bonds, as we're doing over here on the right-hand side, that results in a process where the enthalpy change that we need to worry about is one that releases energy. Okay, so always remember, breaking bonds requires the input of energy. Creating bonds requires the release of energy. So now for this reaction, what am I going to need to know? Well, I need to know 3 bond strengths. I need to know the bond strength of hydrogen. I need to know the bond strength of oxygen, that's a double bond, and I need to know the bond strength of the oxygen-hydrogen bond in water. All right, this first one is fairly well documented. This represents 436 kilojoules per mole for one of those bonds. I'm going to need to break 2 of them, so in fact, in the end, I'm going to have to generate 872. I'm going to have to add 872 kilojoules per mole of energy in order to make this happen here. All right, for the oxygen, this is also well documented, and I think anywhere you look you will find 498 listed as the energy of that bond. There's only 1 of them, so that's the sum total of what I need to create from this, and this is going to account for breaking this bond over here. Now what about the oxygen-hydrogen? Well, you can find listings that seem to suggest that they're showing oxygen-hydrogen for a water molecule or a water-like molecule, but most times you'll find that the value of this bond strength is going to be the average over lots of different molecules, maybe lots of alcohols or other kinds of molecules. In fact, when I looked online, I found that this thing could range anywhere from 459 through 497 kilojoules per mole. I didn't believe all of those, but nevertheless, I think the one that I felt was most reliable gave it a bond strength of 464.6. And in fact, this is one that I think is going to match our results best also. All right, so these are the bond strengths that are involved here. So if I want to estimate the enthalpy change for this reaction, what I would do is add up the amount of energy I have to add to break the bonds. So this enthalpy change, and I'm going to not give it equal, but sort of an approximate sign, is going to be the energy to break 2 hydrogen-hydrogen bonds plus the energy to break 1 oxygen-oxygen double bond. And then I'm going to get back the energy of 4 oxygen-hydrogen bond. So I'll have -4 times the dissociation of the oxygen-hydrogen bond. So this little bit of arithmetic would involve 872 plus 498 minus 4 times this, and the number that I get is 1,857.6 when I add all those things up. All right, so the final result of this is going to give me an answer that looks like minus 487.6. All right. Now, if you were paying close attention to another video, you may have realized that in fact to create two water molecules, as I've done here, this is essentially twice the heat of formation of water in the gas phase. Okay, so let's write it like this. And so that's going to be actually minus 483.6. So I've got two different answers here. And the question is, why am I getting those two different answers, and is there something I can do about it? Well, I'll say that there's two major contributions to this difference. Okay, the first of all is that, and I was talking about this at the beginning, I was using average bond energies. And average bond energies, sometimes they are all about the average, sometimes they can vary quite a bit. And in fact, you'll find in general for carbon-hydrogen bonds that they can vary anywhere from 375 to 450 kilojoules per mole. So the average value of 413 is only going to be good for a small handful of molecules. All right, so these average bond strengths, I should have finished writing strengths, are not exact. And because they're not exact, that actually is a leading cause of error when we use those to estimate the enthalpy change of a reaction. But there's a second source, and this one that I want you to be aware of, and that is that when we talk about the difference in bond energies, this is a very primitive way of looking at energy in a reaction. And the reason I say this is because this, in effect, is basically equating the reaction to taking place at a temperature of 0 Kelvin. That is to say, there's no other place where energy is being stored in these molecules. We are only looking at the energy in those bonds, and yet we do know inherently that there are other places where molecules store energy. So a way to think about this is that we've taken two hydrogens and one oxygen, and these are at, say, 300 Kelvin. And I'm interested in determining what is delta H for turning those into two water molecules, also at 300 Kelvin. But the method that I've used has basically gone down here to say, I'm going to take these molecules at temperature of 0 K, I'm going to break them apart. So this is going to be just the bond energies, and then I'm going to create water at a temperature of 0 K, and I'm going to somehow say that that's the same as that. So this thing that I haven't written in here, this is just bond energies that take me from here to here. All right, but this pathway, as it turns out, if I don't add something for this and for this parts of the pathway, I cannot just equate this to this, and that's in essence what we do in many cases. So this is maybe a leading cause for why we can't really just use bond energies. They often can be a very good approximation, but because of these two different contributions, they're almost never going to give you an exact answer. Now I want to finish by doing what I hope you'll consider to be an interesting exercise, and that is, what if I were to take the information that we've got here and use it to estimate what might be an effective bond energy for the OH bond at 300 Kelvin. So what do I mean by that? Well, let's suppose that I've got my two H2s and my O2, and I'm going to break them apart and just form all atoms. Okay, so I've basically broken up all of these atoms, and I'm going to assume also that probably these bond energies might have been measured at 300 K. So in fact, they don't represent a 0 K thing, but they do contain other aspects of the bond energy. Now, when I add those bond energies together, I end up with a value of 300 kilojoules per mole to get me down to a state of all atoms. Now, when I take all of these atoms and use them to build two water molecules, all right, in essence, the only difference here is the bond energies of the various oxygen-hydrogen bonds. So that's 4 bond energies for oxygen-hydrogen. But now this whole process is equivalent in a way to this process of 2 delta FH0 for water that I'm interested in. But now, instead of assuming that I know this value, I'm going to use the value that we actually do know for this, okay, namely this figure of minus 483.6. Okay, these two things are equal to each other. I'm going to use that value and the values that I've got for these two bond energies that are indisputably easy to measure and ones that we can measure at 300 K, and use all of that to determine what the bond energy for this should be. So, for example, what I'll have is that the total enthalpy minus 483.6 must be equal to 1370, okay, minus, I'm creating these things, minus 4 times the thing that I want, so I'll just call that 4x. And when I solve for x, this simple algebraic equation, what I'll find is that x, which is in effect my oxygen-hydrogen bond strength, is equal to 463.6. So it's 1 kilojoule per mole different from the value that we took from the table. All right. So in this case, actually, sorry, 0.4. So it's a little bit more than kilojoule. Okay, but in this case, what we get is something that we could say represents the value that we might get at 300 K if we were using that in some kind of bond energy calculation to get the enthalpy strength. The bottom line here is use the tables for the enthalpy values. The bond energies can give you a good estimate, but it won't be an accurate estimate in some cases.